Hello everyone, my name is Jaji Chakraborty and I am a PhD student at the University of California, Santa Cruz. I am advised by Professor Carlos Malzain from the CSC department. Today, I am going to talk about our project SkyhookDM, an Arrow native storage system. Let's start by understanding what the broader problem is. In the modern era with the high-speed network and storage devices like InfiniBand networks and NVMe devices with microsecond latencies, I/O is no more a bottleneck, and the bottleneck has completely shifted to the CPU. Client-side computation of data, like reading data from storage formats like Parquet, ORC, and reading and decoding, decompression, all these steps exhaust the client CPUs. The CPUs are no more capable of keeping up with the high throughput of the high-speed I/O devices. This has resulted in highly hampered latency and scalability of distributed data processing systems. One solution to this problem is computational storage. What is computational storage? In computational storage, we offload computation from the client layer to the storage layer as much as possible. In, in data processing systems or storage systems, the storage layer is often present in a data center where the nodes can be scaled dynamically and there are a lot more resources available than on the client side. And even though a lot more resources are available, like a lot more CPUs are available, in case of storage systems, these CPUs are left idle and are not used as much as they should be. With computational storage, we utilize the idle CPUs of storage systems to increase the processing rates and make the queries much faster. And hence, a very less amount of data, only the resultant data you can say, moves around the system. This results in much less memory copying and network traffic. Memory copies are a big issue in data processing systems along with serialization. So the lesser the data movement, the lesser the overheads of memory copying and serialization deserialization. The current implementation of Skyhook builds on the Ceph storage system. So let's start by discussing Ceph. Ceph is a distributed object storage system and it provides three types of storage interface: a file system interface, a object store interface, and a block device interface. Interfaces interact with Rados via a single channel called libRados, which is a library for allowing apps to directly access the Rados layer and has support for writing in C++, Java, Python, etc. In Ceph, there is no central point of failure. Ceph does this by using crush maps, which are basically object OSD mappings. When a client connects to a Ceph cluster, the crush maps are downloaded to the client, and from the crush maps, the clients can figure out the locations of the objects within the distributed Ceph storage layer. Also, Ceph is highly extensible. Basically, the object storage layer in Ceph, which is Rados, is highly extensible thanks to the Ceph object classes SDK. We will look at the object class SDK next in more detail. The Ceph object class mechanism. The Ceph object class SDK is a object store extension mechanism that allows customizing or modifying the I/O path in Ceph by writing plugins in C++ and by embedding the built shared libraries in every storage node. The object class mechanism is used by several internal Ceph systems like CephFS, Rados Gateway, and Rados Block Device. The Ceph object classes are present in the Ceph source code at ceph/source/cls and has and there are quite a lot of Ceph object classes that has been contributed to Ceph over the years. As you can see, the growth of object classes in Ceph over the years in this chart below. Another piece of software central to Skyhook is Apache Arrow. Apache Arrow is a language independent columnar memory format for flat and hierarchical data organized for efficient analytics operations on modern CPU hardware. So Apache Arrow is basically a common standard memory format for exchanging data between different data processing systems. Without Arrow, different data processing systems generally need to convert the data between their customized internal formats, and this requires a lot of memory copy and serialization deserialization over it. But with Apache Arrow data, as long as all the different distributed data processing systems understand Apache Arrow data, the data does not need to be converted or copied for transmitting between different systems. What else is Apache Arrow? Apache Arrow, besides being a highly efficient in-memory data format, it is also a rich collection of pluggable components that can be used for building big data processing systems. Apache Arrow is aiming to build a data processing framework where different of its APIs can be plugged in or glued to build a data processing system. Apache Arrow provides interfaces like an embeddable query engine, a multi-threading runtime, a datasets framework, a data frame framework, different compute APIs, a LLVM expression compiler, a binary protocol to move data between different systems, memory allocators, buffers, you name it. Apache Arrow has it all for building data processing systems. Apache Arrow can also work with different file format interfaces like Parquet, Avro, CSV, JSON, ORC, which are the most common in the data processing landscape. It can read data from different file systems apart from local file systems like HDFS, S3, Azure, GCP, all the cloud file systems. We use several of these embeddable components from Apache Arrow for building Skyhook. Next, let's look at the design paradigm behind building Skyhook. The idea behind Skyhook is to extend the storage and client libraries of storage systems by embedding data access libraries so that data can be processed directly inside the storage layer, and that feature can be exposed via extending the client-side APIs of data access libraries. We extend the client and storage layers of programmable storage systems with data access libraries like Apache Arrow. In Skyhook, we create a file system shim inside the storage nodes, which provides a file-like view over the objects or blobs inside the object store. And we allow direct interaction with the objects from the client by bypassing the file system layer. So how this works is that we see files in file systems, and when the requests are launched using Skyhook, we convert the file names to object IDs using file system metadata like striping strategies. And we directly interact with the objects in the object store by invoking the Ceph plugins, the object class plugins that we embedded inside the OSDs. This object class plugin uses Apache Arrow to process the data and sends us back serialized arrow tables. Now next, let's look at the architecture of Skyhook. In Skyhook, we use Ceph as the base storage system. We embed Arrow data access libraries, basically the Arrow Dataset API, inside the Ceph OSDs to allow scanning data blobs from the Rados object store. We scan the data blobs from the Rados object store and get back arrow tables, which we serialize and send back via the Arrow Dataset API to the client. On the client side, we implemented a Skyhook file format, which extends the file format API in Apache Arrow. And what it does is that instead of reading from Ceph via the file system, it bypasses the file system layer and invokes the Ceph object class plugins or the Skyhook plugins and uses Apache Arrow to do the processing and reading inside the storage layer and just receives back the serialized Arrow tables as results. Let's now talk about the file layout design in Skyhook. In Skyhook, we found out that 16 MB is often the file size that gives us the best results in later with different file sizes. Like we ran a parameter sweep over different file sizes from 4 MB to 128 from 4 MB to 128 MB in powers of 2, and we found out that 16 MB files give the best results in terms of latency. The files that are larger than 16 MB are splitted into smaller files of 16 MB, and each file is stored in a single Rados object. This is done during the write phase in Skyhook. Since we use the Arrow Dataset API inside the storage layer of Skyhook, we get access to different file formats like IPC, Parquet, CSV out of the box. Hence, Skyhook can be used on different datasets having different files of different formats like IPC, Parquet, CSV, etc. Let's understand the file layout design of Skyhook. For example, if there is a large Parquet file called abc.parquet with several row groups and its own footer metadata and the footer and header magic bytes, when we write this file into Skyhook, the files are splitted into 16 MB smaller Parquet files with just a single row group, its own footer metadata, and the header and footer magic bytes. So these splitted files are also Parquet files, but just having a single row group, and they are mapped to a single Rados object. This single one-to-one mapping of Parquet files to Rados objects is guaranteed in Skyhook. Let's look at the results that we get from the experiments that we did with Skyhook. First, we measured the CPU usage over an entire experiment duration with and without Skyhook. Without Skyhook, when we just did client-side processing of Parquet data, we found out that the client CPUs were totally used and the performance was bottlenecked by the CPU, while the storage CPUs were almost unutilized as there is no processing going on and only there is read and write IO on the storage layer. But with Skyhook, what we did is that we offloaded the CPU usage from the client to the storage layer, and immediately the client side got much relieved, and while the CPU usage got nicely distributed between the 4 storage nodes that we had. We also found out that there was a significant latency improvement on offloading with Skyhook in cases of higher selectivities, like 1% or 10% of the rows. Next, we also measured network bandwidth usage while running data processing queries with Skyhook. We found out that with higher selectivities, like with 1% and 10%, the much less network bandwidth was used, as only the filtered data, only 1% of the rows or 10% of the rows was coming back to the client. While in the green lines, without Skyhook, in every selectivities, all the data was just retrieved from the storage layer to the client for processing, and hence the network bandwidth was always the same. There is a little catch in the 100% case where we see that Skyhook uses more network bandwidth. This is because Skyhook returns the results in Apache Arrow format, in LZ4 compressed Apache Arrow format, which is larger in size than highly encoded Parquet binary data. So that's the reason why in the case of 100% scenario, the network bandwidth is a little bit more in Skyhook than without Skyhook. Another nice thing that we get complementary with Skyhook is automatic failure recovery. In Skyhook, since we co-locate compute with the storage nodes, the failure recovery and consistency semantics of storage systems, of distributed storage systems like Ceph, apply naturally to the compute layer. So if a storage node fails in the middle and the query also stops, after the storage node comes back up by its own failure recovery semantics, the query request is retried again and the computation happens from the beginning, and thus we don't need to develop any complex failure recovery semantics for the compute layer. For example, in the chart that you see below, we ran an experiment for 250 seconds, and in about the middle of the experiment, we crashed all the storage nodes one by one. As you can see, the network throughput dropped down from around 300 to less than 50, and just after a while, all the nodes started coming back up again, and the computation resumed perfectly, and we got back to the point where we crashed. Thank you very much for listening to my talk. Please take a moment to rate this session.